ಕಿರಣ್ ಗೌಡ್ರ ಸರ್.
ಕಿರಣ್ ಗೌಡರ್. ಹಾಂ, ಓಕೆ ಓಕೆ ಓಕೆ. Good morning, everyone.
Sir, Naveen Gowda Patil has joined.
Joined? Okay. So I'll speak to him after the class. Okay, last 1 minute I'll speak to him. So let us continue today's class. So before we start the class, so it's my pleasure, it's my fortunate today that I'm wishing my lovely boy, my lovely student, Kiran, let him be a winner, let him be an achiever. So I wish a very happy birthday on his special day. So let him grab whatever knowledge you want to acquire. After acquiring, let him conquer any height of his wish. So let him come out as a successful person in the society, because ultimately in the society we want to lead a comfortable, happy life, whether it is a self or with others. Okay, so I wish him once again a very happy birthday and best of luck, fruitful days ahead next year 12th class, and we wish him that he will be in the India campus, so with all clearing all the obstacles, UPC obstacle, then medical fitness, everything conference, so he will come out successfully with uniform. Okay, so and I also wish if Sushmita joins the India campus along with Kiran, so for Kiran it is a birthday wish, and for Sushmita it is the first girl to enter the India campus. Okay, so with this let us start today's class on the ionization enthalpy. So this was the point of discussion. Now today we will go to this slide. Successive ionization enthalpies for period 3. So period 3 is what? Period 3 starts from sodium, atomic number 11.
Sir, is it recording?
Recording started. Okay, it is already a process. Good, very good.
Okay.
Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Period number 3rd. Second period starts from lithium and ends with neon. Third period starts from sodium and ends with argon. Okay, so all these are successive ionization enthalpies or energies for third period. So just have a glance, because there are data, no need to by heart, just you have to analyze, you have to understand. So from what we gain from this table, so it is easy to remove the first electron. As we go second or third, it becomes difficulty. This I told yesterday. So you can concentrate on the shaded part, that yellowish orange type of color I have given. So that part is very difficult part too. That is to remove electron. So for the sodium to remove second is very difficult. Okay, when second is very difficult, then we will not think of third and the fourth, third onwards. Okay, so in the case of argon, you see, in the case of argon, so 12,000 IE7. So that means what we feel, argon is very easier to remove electrons. So stable, no, it is stable. So once we disturb the stability, they become unstable. First of all, they are stable, so by nature. So due to some reasons, if they become unstable, then they also start losing electrons under some special conditions. Okay, right. So that's the idea behind this table. So go through in the free time. So now have an idea only. So no need to go in detail about this table. So removing 1, 2, 3 very easy. Beyond 3 very difficult. That is the idea. Now factors affecting IE. IE is what? Ionization enthalpy or energy. So every time I not use ionization enthalpy, I use IE. So on what factors IE depends? Factor number 1, effective nuclear charge. What is effective nuclear charge? It is the total charge of the nucleus, okay, on the electrons, because the one which is close to the nucleus will have more impact, and the one which is away from the nucleus will have less impact. Okay, but less plus more by 2, that is called average. That is what? That is called effective nuclear charge. How much nuclear charge is effective on electron? What kind of effect? Attractive force. Okay. How much it is holding? How much it is attracting? How much it is pulling towards itself? That is called effective nuclear charge. Okay. And if the nuclear charge is more, holding is more, attractive force is more, electron is attracted towards nucleus more, that time we have to face what? Difficulty in removing the electron. That means what? We require more energy. So more the effective nuclear charge, more is its ionization enthalpy. That's why I have written IE is directly proportional to Z effective. Z is what? Effective nuclear charge. Okay, so Z is nuclear charge, EWF is effective. So effective nuclear charge Z symbolically. Okay, symbolically. So directly proportional. More the effective nuclear charge, more is the charge. That's the idea. So examples are also there at the bottom, and which has given the clear cut support for this factor. That is lithium's IE is more than beryllium. Lithium is 2 1, beryllium is 2 2. So lithium is towards left side of the beryllium, or beryllium is the right side of the lithium. If you see the second period on the modern periodic table, their positions. Okay, so that means if you move from lithium to beryllium, that means you are moving from left to right. When we move from left to right, what happens regarding the atomic size or the effective nuclear charge? So it will increase. So because effective nuclear charge is increasing from left to bottom, left to right, that's why it is very difficult to remove electron from the outermost shell when you move from left to right. So because we are moving from left to right from lithium to beryllium, so beryllium will have more IE, very clearly shown this effect. Second example I have taken was boron, carbon and the nitrogen. Boron atomic number 5, carbon 6, nitrogen 7. So when you are moving from boron to nitrogen, you are moving from left to right, same reason. Left to right, increase in the effective nuclear charge, so increase in the IE. And the second factor is size of atom. So more the size, electron goes far away from the nucleus. When electron goes far away from the nucleus, less attractive force between the nucleus and the electron. When less attractive force between an electron and the nucleus, less effort to take out the electron. So it is inverse relation. More the size, less is the IE. That's why the red rectangle equation is there, word equation. So IE is inversely proportional to size. Okay. So three examples are there. Lithium, sodium, potassium, rubidium, cesium belongs to extreme left first group. So as you move from top to bottom, size is increasing. Definitely IE decreases. In the same way, second example is beryllium, magnesium, calcium, strontium, barium. They belongs to second extreme left, second group, alkaline earth metals. There also we are moving from top to bottom only. So when we move from top to bottom, extra shells are created. So new size increases, electron goes far away, control is less, so less IE. All those are related. Third example is fluorine, chlorine, bromine and the iodine under the group 17 known as what? Halogen group. So here also we are moving from top to bottom. Say for all the three, same reason. What is the reason? Increase in the atomic size decreases the IE. Charge. IE is proportional to the ratio of positive charge to negative charge. If you want IE should increase, the numerator should be more. What is numerator here? Numerator is plus charge. If the plus charge is more, so whenever you have to calculate. So here we are discussing theoretically in the class, but when you go to the exact laboratory level or the spectroscopical level, that time we exactly calculate how much positive charge is there, the negative charge is there. We go for a ratio. So if the answer is if the positive charge is more, numerator is more, answer is positive, the term what happens here? It is directly proportional. Means what? I becomes more. Okay, so increase in the positive charge increase the, what is positive charge? It is very related to the effective nuclear charge only. Both are almost same. So you can see examples here at the bottom. So Li has got less IE than the Li plus. Li is neutral, whereas Li plus is what? Charged. So taking out electron from the neutral is very easier than the plus atmosphere. So therefore Li plus will have more IE than Li. Second, He less than He plus. Plus charge is there. I told you, no, more the plus charge, more difficulty. Okay. And more IE. Third example, Mg plus, Mg2 plus. Mg2 plus, 2 plus charge. Small size. Okay. So definitely we will have more IE. Fourth example, aluminum. Aluminum 1 plus, Al2 plus, Al3 plus. Al3 plus very small, high charge. Okay. Very high IE. Fifth one you see, O minus 2. You please here, charge is there, but when the charge is plus, size becomes less. When the charge is minus, size becomes more. Why? Electrons are added. When the electrons are added, so either electron has to enter in the same level. There are two possibilities when you add electron. What is the possibility number one? Possibility number one is what? Either it will enter in the same level or it can go for the new shell. Okay, whether it is entering in the same level or in the extra shell, size has to increase, because once the electron enters in the same level, so already there are some electrons. So with existing electrons, this extra electron you are adding, so thereby they go for the inter-electronic repulsions. So due to the inter-electronic repulsions, size may expand to some extent. Or if electron is directly added to the last shell, then when the new shell is created, then no doubt at all it is going far away. Okay, so size will increase, no doubt. So increase the size, decreases the IE. So here charge is very important. I told you, if the plus charge is more, IE is more. Negative charge is more, IE is less. So negative is at the bottom, positive is on the top numerator in the equation. Okay, in the same way, sixth example is what? N more than N minus, more than N minus 2, more than N minus 3 nitride. So N minus 3 is what is nitride. Nitride has got very less sorry, that's more IE, because it is bigger compared to any nitrogen species. Okay, so all those we understood when you understand the ratio between the plus and the minus related to the IE. Next factor is electronic configuration. More stable the electronic configuration, more is the IE. Why more IE? Because when the stability is there, so they don't want to lose or they don't want to gain. They are the stable condition, haram condition. Why to disturb? So to disturb, you have to spend more time, more energy, more physical labor. So now let us compare nitrogen and the oxygen. Nitrogen is what? 1s2, 2s2, 2p3. Oxygen is 1s2, 2s2, 2p4. So here we have to worry about 2p3 and 2p4. 2p3, how to arrange 3 electrons in the 2p3 in the 2p according to above, according to Pauli, and according to Hunds. So 1 electron in each 2p subshells, 2px1, 2py1, 2pz1. So each subshell of 2p will take 1 electron, because space is available. No, Hund's rule, as long as space is available, they will not prefer to go for the pairing. Only in the case of oxygen, 4th electron has to go for pairing, no other way. Okay, no option for the 4th electron. It has to go for pairing. So in the case of oxygen, it is 2px2, 2py1, 2pz1. Whereas in the case of nitrogen, it is 2px1, 2py1, 2pz1, which is called as half-filled electronic configuration, which is stable. Please recall our structure of atom topic chapter, where we learnt stability of the half-filled and stability of the fully filled. So when we compare nitrogen with oxygen, so nitrogen is half-filled, more stable, so more IE. That's why it is said that electronic configuration plays very important factor in deciding the IE. Now in the same way, phosphorus and the sulfur are explained. The next factor, penetration effect. Penetration is using the needle. I am penetrating the paper or the cloth. That is called penetration. One more example, X-rays are penetrating into our flesh area. Whenever you go for the X-ray for the to exactly identify the fracture part, so those X-rays will go into the flesh part. Okay, flesh it can interact, it will go, it will pass through, but with the bones it will not. Bones are very hard. So because they are not passing through the bones, so they will give shade. The image is on the screen that doctor can analyze and he will come to know that this area fracture or the crack is there. So that is what is called as penetration. Here, what is the penetration effect in the IE? Okay, so here penetration we have to think in which angle, how much time electron is going close to the nucleus. That is called penetration. So the more it goes close to the nucleus, the more it is penetrating towards the nucleus. That is the meaning behind the penetration effect of this today's topic. Okay, not that needle penetration or not that extra penetration. Okay, extra also going close, like that. So that is the idea. So we take that meaning here. Okay, so that's why I gave those two examples. So penetration here means what? Spending more time or going close towards the nucleus. For this, we have to understand the shapes of atomic orbitals. Okay, so when we understand the shapes of atomic orbitals and other factors also, that time we can apply this penetration effect. Normally, in general, there are some odd cases, there are some exceptions, because in science we say a rule, we make a rule. These general rules are there, but that doesn't mean that it should be applicable 100%. All metals are solids. Again, mercury comes in between. Okay, so like that, there are some exceptions are there. There are some odd cases are there. So we will not apply all those. So in general speaking, by looking to the shapes of atomic orbitals, S orbital is spherical, round. Therefore, it is penetrating more towards the nucleus. That means what? It is moving around the nucleus very close to nucleus. In 3D, you have to imagine. Okay, not in 2D. So when you imagine in 3D to our mental picture, so due to its nature, shape, by the Schrodinger's wave equation, all those psi we have solved equation, wave function. So it is spending more time towards the nucleus. So any electron which is there in the S will have more penetration, more close to nucleus. Then very difficult to remove electron. Why it is close to nucleus? No, when it is close to nucleus, so attractive force is more. When the attractive force is more, you require more energy to remove all those. So chain reaction. So S is more close, then comes P because dumbbell shape, then D double dumbbell, it is spread in the space, so little far away. F is again most complicated lobes are there. So as we move from S to P to D to F, so penetration is decreasing. Okay, so that means as the penetration is decreasing, IE, what happens? I also decreases. It is the S electron spending more time near the nucleus will have more IE due to its shape. General, once again I am reminding you, general. Okay. Now examples you see here. Beryllium is more than boron. What is beryllium? 1s2, 2s2. What is boron? 1s2, 2s2, 2p1. 2p1. Okay. So in the beryllium, there are two reasons in the beryllium. Reason number one is what? Beryllium, it is S electron. Fourth electron is S. S is what? Spending more time, penetrating towards nucleus more time. Okay. So it is having more close to nucleus, more energy. So we require more energy to remove the electron. So beryllium is more. Second reason is what? 1s to 2s. Both are completely filled, no? Both orbitals are completely filled. Again, extra stability. So due to these two reasons, beryllium will have more IE, whereas in the boron, it is 1s2, 2s2, 2p1. That single electron is in the P, slightly away from the nucleus. Okay, so slightly away, and the penetration is less compared to S orbital. Therefore, we'll have less energy. So all these you have to find out. So in the nature, something is happening. Only thing, what is our duty? What is our learning area? Why it is happening? Okay, and when you come to the conclusion, when you take out the reasons, you'll enjoy the science. Okay, right. Now, second example is magnesium, aluminum. Magnesium, atomic number 12, 1s2, 2s2, 2p6, and 2s2. Again, s orbital is full, right? And s orbital close to nucleus. Same reason you can quote between magnesium and the aluminum. Now we'll go to the one more small part, that is what? Variation of IE in S and the P block. Okay. So how in S and P the variation changes are there, how it varies, okay, in the S and the P only. So D and F we learn in the 12th class more, not in the 11th class. So in S and P only we learn, that means we apply the knowledge of IE for the S block and the P block elements. Right. You please here. S block and the P blocks I brought here. Okay, S block lithium to cesium, S block beryllium to barium, top to bottom. Okay, then P block boron to tellurium, carbon to lead, nitrogen to bismuth, oxygen to polonium, fluorine to astatine, neon to radon. So top to bottom. So first group, second group directly it is 13th group because in between D block is there. So boron 13, carbon 14, nitrogen 15, oxygen 16, fluorine 17, and the last one neon 18th group. Okay. So these two are called what? Representative elements S and P blocks. So what is the impact of IE in these two blocks? In these two blocks. So I have shown arrow mark from left to right, arrow mark. So effective nuclear charge is increasing. Effective nuclear charge is increasing. So when the effective nuclear charge is increasing, automatically IE increases due to the small size or due to the control by the nucleus over the electrons. But when you move from top to bottom, the downward arrow mark, okay, so the size is increasing. So increasing the size decreases the IE. This is general. But at the right side of the slide, I have given some examples. Beryllium more than boron, magnesium more than aluminum, calcium I is more than gallium, nitrogen is more than oxygen, okay, phosphorus more than sulfur, arsenic more than selenium, top to bottom, aluminum, gallium, due to third contraction in gallium, okay. So what is third contraction here? 3D, not the 3D contraction, okay. So when we, there's one more area, when we move from S to P block via D, this happens from where? From the scandium. Okay, so potassium is 19 and 20 is calcium, 21st is scandium. So from the scandium, D block starts, which is not shown here. Okay, so there D entry is there, 3D entry. So that 3D entry will have some trouble, will give some trouble. So they cover what the outer electrons. That means they protect the outer electrons. So because they are protecting the outer electrons, so nucleus will have less control over the outer electrons. So when the nucleus has less control, you can remove electron, okay, easily. Otherwise, if they don't cover properly due to the shapes, that time they are pulled towards the nucleus. If they cover properly, nucleus will not have control over the outer electrons. If the D and the F are covering properly, then when they cover properly, they are less control. When they don't cover properly, then they are pulled by the nucleus. Both effects are called as what? Shielding effect. Okay. So this will learn in the what again 12th class. But what is shielding effect? Shielding effect is what is shield here? Shield is to protect something. You might have seen in the museums. Uh, Salar Singh Museum, or if you visit Bijapur's famous Gola Gumbaz, okay, so there in front of the Gola Gumbaz there is a museum where we will see the old articles, old things, items are there, which they are using for the war, okay. So you can see some shield, okay, in the hand, they use it for the war, they protect arrows. When the arrows comes, we will hold that shield. That is, it is called as a protector for our body. We wear something on the body also with chains, with the metals. So that any arrow will come and hit, it will not hurt. Okay. So all those are called what? Protective covers. They are shielding our body. They are covering our body. In the same way, if the d electrons or the f electrons, they shield, they cover outer electrons. Okay, that means d are inside. When you see the energy level diagram of the above, d is inside. So the inner d electrons, if they cover properly the outer electrons, then nucleus will not drag. If they don't cover, then they drag. So this effect is called as what? Shielding effect by the inner electrons over the outer electrons. Okay. So that is what? Shielding effect. Right. So all these examples are related to this comes when D entry is there. If F entry is there, this effect is still more because of the shape. Okay. F shape. Now graphic also we can see, you can go through whether it is increasing trend, decreasing trend, all those trends you can see graphically when you are free. Okay, not to be by hearted, just to understand. See once again, hydrogen to the water, magnesium, hydrogen, helium, lithium, beryllium, carbon in a particular period. Okay, so why in between some hiccups are there, all that you will understand on many grounds, penetration ground, half filled ground. So many grounds are there, you can explain. So what is the conclusion? Conclusion is what? Left to right IE increases, and from bottom to top IE increase, or from top to bottom IE decrease, from right to left IE left to not right to left it will decrease, left to right increase, right to left decrease, top to bottom increase, bottom to top, sorry, top to bottom decrease, bottom to top increase. So you please see the red arrow mark, it will give idea. So on what ground they are increasing, that you have to analyze by applying all those factors affecting the IE. Same diagram I have to discuss once again. See, just idea about the shielding effect, how the inner electrons play very important role for the outer electrons. So just to have an idea, so I made this. So in moving around the nucleus, they are indirectly covering the outer electrons. If they cover properly, no problem, otherwise problems are there. This is called what? Shielding effect. Just to understand, 12th class we study in detail. This is what is effective nuclear charge. Okay, so when the effective nuclear charge is more, it will control, otherwise it will not control, electron is removed easily. That is the idea behind. So remaining part we will discuss later. So I think we wind up today's session. Almost it's now 12, 10, 11 ho gaya. So 1 minute extra, but still my Webex is saying that some time is there to end. So if at all any doubts till now, whatever we have studied, so happy to share with you whatever I am having. So I want to try to answer all your queries. If at all any doubt either, if doubt is not there, if everything is clear, I'm very happy with live interactions. If you can make my topic very clear and practice by reading the textbook, very fantastic. So most welcome for about 2 minutes. Navin Gada,
Yes, sir.
please wait. Okay.
Yes,
So
sir.
I think no doubt. So we'll wind up.
Mm.
You can join. I will speak to Navin Gada later. You also can join, no problem. It's a open discussion. Okay. So right. Okay. I will going to stop. Thank you and all.